Evaluating Occam's razor in the acceptance of scientific and philosophical theories, a logistic regression approach. This video explores the role of Occam's razor, OR, in determining the acceptance of both scientific and philosophical theories, focusing on speculative and non-mature ideas in physics, biology, and philosophy. A logistic regression model, developed in collaboration with ChatGPT and based on the editor's instructions, predicts the likelihood of theory acceptance based on OR challenge, empirical, philosophical success, and data-driven levels. The analysis also introduces the concept of false rejection, where theories may be prematurely rejected based on OR despite their future potential or conceptual viability. 1. Introduction. Occam's razor plays a pivotal role in theory acceptance across various disciplines, but it often leads to premature rejection of speculative theories. Throughout this research, the editor's prompts focused on whether OR is used too early in speculative fields, particularly in theoretical physics and philosophy. Together with ChatGPT, the focus was placed on identifying the role of false rejection where potentially viable theories are dismissed because they seem overly complex. 2. Dataset and theories selected. Theories were chosen based on the editor's instructions to explore both mature and non-mature ideas, with an emphasis on theories that faced OR challenges during their development. ChatGPT gathered relevant data from various domains, as directed by the editor, to construct a dataset that would illustrate the interaction between OR challenges and the acceptance or rejection of theories. Full dataset of theories. The theories were categorized by maturity, as prompted by the editor. I also incorporated OR challenge and data-driven level measures based on instructions to highlight which theories faced the greatest hurdles from OR. 3. Methodology. This section explains how ChatGPT, built and validated the logistic regression model based on the editor's requests. The process involved. Logistic regression model. The logistic regression model was built to predict the acceptance probability of a theory based on 3 variables: OR challenge, success, and data-driven level. As per the editor's instructions, I implemented the following model. P accepted equals 1 divided by the quantity 1 plus e to the quantity beta sub 0 plus beta sub 1 times OR challenge plus beta sub 2 times success plus beta sub 3 times data-driven level. Where 1. Beta underscore 0, the intercept. 2. Beta underscore 1, beta underscore 2, beta underscore 3, coefficients for OR challenge, success, and data-driven level. The false rejection proxy was added based on the editor's direction to investigate cases where Occam's razor may have wrongly influenced the rejection of a theory. Model validation and robustness. The editor asked for more information on how the model was validated and the robustness of the estimates. In response to that, I used the following techniques. 1. Cross-validation. At the editor's request, I implemented 5-fold cross-validation to test the model on different training and testing subsets of the data. This approach ensured that the model generalized well beyond the specific dataset used for training. 2. Receiver operating characteristic, ROC, curve. The editor asked how well the model could distinguish between accepted and rejected theories. In response, I generated an ROC curve and calculated the area under the curve, AUC. The AUC provided a quantitative measure of the model's discrimination ability, with an AUC closer to 1 indicating good performance. 3. Confusion matrix. The editor prompted me to explore false positives and false negatives, which led to the construction of a confusion matrix. This allowed for the evaluation of key metrics such as precision, recall, and the F1 score, giving a clearer view of the model's accuracy in predicting theory acceptance or rejection. 4. Confidence intervals, 95%. Following the editor's request to determine how stable the estimates were, I calculated confidence intervals for the model's coefficients. These intervals demonstrated the reliability of the estimates for OR challenge, success, and data-driven level. 5. Variance inflation factor, VIF. To ensure that there was no multicollinearity between the variables, per the editor's suggestion, I calculated the VIF. The low VIF values confirmed that the predictors were not too highly correlated, which ensured that the model's coefficients were reliable and independent. 6. Likelihood ratio test and Nagelkerke's R-squared. At the editor's suggestion, I conducted a likelihood ratio test to compare the model's goodness of fit with a null model, confirming that the model provided a better fit for the data. Additionally, I calculated Nagelkerke's R-squared, showing that the model accounted for a meaningful portion of the variance in theory acceptance. 4. Model results and parameters. Here, I presented the results of the logistic regression model and interpreted them based on the editor's questions about how the different factors contribute to theory acceptance. Parameter estimates. Interpretation. 1. OR challenge. Coefficient 1.23. Effect. Theories facing higher OR challenges, more complex or speculative, are less likely to be accepted. The negative coefficient indicates that as the OR challenge increases, the likelihood of acceptance decreases. Odds ratio 0.29. This means that for each unit increase in OR challenge, the odds of a theory being accepted decrease by about 71%. 2. Success. Coefficient plus 2.48. Effect. Theories with higher empirical or philosophical success are more likely to be accepted. The positive coefficient shows that greater success increases the likelihood of acceptance. Odds ratio 11.93. For each unit increase in success, the odds of acceptance increase by a factor of 11.93, or nearly 12 times more likely to be accepted. 3. Data-driven level. Coefficient plus 1.13. Effect. Theories that are more data-driven are more likely to be accepted. The positive coefficient suggests that the more a theory relies on empirical data, the greater its chances of acceptance. Odds ratio 3.09. For each unit increase in the data-driven level, the odds of a theory being accepted are about 3 times higher. 5. False rejection analysis. At the editor's request, I carried out a false rejection analysis to identify theories that may have been wrongly rejected based primarily on Occam's razor. The criteria, as specified by the editor, involved identifying theories that 1. Faced significant OR challenges. 2. Were not replaced by simpler theories. 3. And still hold conceptual value or are debated today. 4. Editor's note. The requested third requirement was that the theory be taken seriously by the respective community. ChatGPT expanded this to theories that are still debated, etc. False rejection results. Key findings. 1. 50% of rejected theories were flagged as false rejections based on the lack of a replacement theory and high OR challenges. 2. Philosophical theories like panpsychism and libertarian free will were identified as false rejections, as they continue to be debated despite initial rejection. By applying the false rejection proxy, we were able to highlight several theories that were prematurely dismissed by OR, as guided by the editor's interest in exploring whether OR is applied too soon in speculative fields. These theories remain contenders in their respective domains, indicating that OR-based rejection may have been premature. 6. Discussion. OR in science and philosophy. The results, as prompted by the editor, indicate that Occam's razor plays a central role in the acceptance or rejection of speculative and non-mature theories, especially in fields like theoretical physics and philosophy. However, this analysis highlights that its premature application often leads to false rejections. These complex theories are frequently dismissed despite their potential for future reconsideration. False rejection in philosophy. Theories in philosophy, such as panpsychism and libertarian free will, are particularly vulnerable to OR challenges because they introduce complex metaphysical concepts. Since empirical data is often lacking in philosophical arguments, these theories are at a higher risk of false rejection. However, they continue to be debated, suggesting that their rejection was based more on simplicity than on actual conceptual failure. The editor's exploration of how OR functions in non-empirical fields was instrumental in shaping this discussion. It shows that while OR works well in more data-driven fields like biology, it may have limited utility when applied to fields like metaphysics, where complexity is inherent to the subject matter. 7. Conclusions. 1. Occam's razor is effective at streamlining theory acceptance in fields like biology, where data and empirical validation are readily available. 1. However, the use of OR in speculative fields like theoretical physics and philosophy can lead to false rejections. 2. Philosophical theories face particularly high risks of being falsely rejected due to their speculative nature and the lack of clear empirical evidence. 3. There is a need to re-evaluate speculative theories as conceptual and empirical frameworks evolve, especially in fields where future advancements could provide the necessary support for these theories. 8. Recommendations. 1. Reassess Occam's razor in philosophy. OR should be applied more cautiously in philosophical discussions, where empirical evidence is less central to theory acceptance. 1. As the editor suggested, philosophical theories may require more nuanced evaluation beyond the simplicity criterion of OR. 2. Revisit rejected theories. Based on the editor's interest in false rejection, theories that were prematurely rejected on OR grounds, such as panpsychism and supersymmetry, should be re-examined periodically. 2. As fields evolve, these theories may gain conceptual or empirical support. 3. Develop a balanced approach for OR. OR is a valuable tool, but its over-reliance in speculative fields can stifle innovation. 3. A more balanced approach that considers both simplicity and theoretical potential is necessary, as prompted by the editor's exploration into whether OR is being applied too soon. Conclusion of process. In this collaboration between the editor and ChatGPT, 1. Prompts from the editor guided the selection of theories, the methodological framework, and the focus on speculative and philosophical theories facing OR challenges. 2. Logistic regression modeling, validation techniques, and false rejection criteria were applied based on specific instructions to examine the impact of OR on theory rejection. 3. The dataset was curated to reflect the editor's focus on distinguishing between mature, non-mature, and philosophical theories. 4. The final analysis provides insights into when Occam's razor may be applied too early and highlights areas for future research, as requested by the editor. This document reflects how the analysis was shaped by these guiding prompts, and how each step was validated to meet the editor's objectives. Editor's note: I had started with a model to estimate the utility of OR based on variables used in this analysis and whether the theories had been accepted or not, and realized during my discussions with ChatGPT that the model technique was biased. ChatGPT didn't notice the biased nature of the technique until I pointed it out. At this point, I discussed the hypothesis I wanted to test and the variables that I thought were important. ChatGPT suggested the logistic regression and proposed a very indirect approach to testing the hypothesis. That is when I introduced the idea of a proxy for the possible premature rejection of a theory, i.e., the false rejection. ChatGPT and I have gone around and around about the data. We had twice the data that show up in this analysis, but ChatGPT would lose part of it at each reconsideration of our analysis. ChatGPT would often complain that the environment had been reset, and it was necessary to reconstitute it. In summary, working with ChatGPT on this video would have been entirely delightful had what I think are technical complications not interfered with the analysis. I found myself always afraid that important pieces of the project would be lost. ChatGPT has certain weaknesses and blind spots. For instance, ChatGPT will make an assumption about an argument, much like a person will sometimes do, and completely misconstrue the import. When the clear signals of the direction of the argument are pointed out, ChatGPT will acknowledge the oversight and say that it had judged the argument perfunctorily because the argument was similar to another it had encountered. ChatGPT will do this on the same argument every time. That breaks the anthropic illusion, and makes working with ChatGPT less fun. ChatGPT is very much a creature of the status quo, but it can expand on a novel idea to some extent. The present vehicle for ChatGPT is insufficient for significant research tasks. A dedicated platform may work, but how many of the shortcomings are innate, and how many are technical is not clear. But I would recommend giving it a try. PSI note that ChatGPT left out the accepted estimates. This kind of oversight is common for this platform. I do not know whether it is the nature of large language models or simply a technical matter. But here are the values.